This is the second video for partial fraction decomposition and calculus. And we're going to spend a little time talking about the difference between linear factors, repeated linear factors, quadratic factors, and then there's also repeated quadratic factors. So I set up these three problems here so that you could practice naming the type of factor. So if I just had an x minus 1 factor, hopefully you know what type of factor that is. It is a linear factor. It is not repeated because there's no squared up there or cubed or to the fourth or the fifth. It's just x minus 1 to the first. So it is just a linear factor. This, because it's degree 2, is a quadratic factor. Anytime you have a quadratic factor, you should try to factor it into linear factors. But this, if you tried to work out two factors of this is non-factorable, so it would be considered a quadratic factor. If you had any factor higher than that, there would be a way to factor it into quadratic or linear factors. So you only have to worry about quadratic and linear down here, not cubic. So in this case, I would say that the partial fraction has one linear factor and one quadratic factor, neither of which are repeated. If you went to set up the decomposition for it, you would need one fraction with x minus 1 on the bottom and another fraction with x squared plus x plus 1 on the bottom. And both of those have to be proper fractions. So when you go to put the constants on top, since this is x minus 1, degree 1, then this must be a degree less than 1, so it's degree 0. I could say x to the 0, but I don't need that since x to the 0 is just 1. But now, since this is a quadratic factor, then I have to put a linear factor on top. So b or c might be 0 when you work out the algebra for it, but they might not be. And see how both of these are proper fractions, and the structure of what this can split up into when it is written as the sum of two fractions could be as complicated as this. It might be less complicated, but it won't be more complicated than this, meaning that there can only be two distinct fractions, and this one can only have a constant in the numerator, and this one can only have a linear function in the numerator. Quadratic on the bottom means that the numerator can be linear. So if you had to, we're not going to take the time to work out the solution to solve for a, b, and c right now, and I'm not sure that this will come out to be a very friendly problem, so I wouldn't recommend trying it. I'm just trying to give you some examples of the setup. All right, so looking at this one, you're trying to decide which type of factors you have. X squared plus 4, you would consider trying to factor that sum, but it definitely doesn't factor anymore. So it is a quadratic factor, and it is repeated. So this fraction only has a repeated quadratic factor. If you tried to break that into the sum of two fractions, one fraction could have just one factor of x squared plus 4. Now you might think that that would be enough, but if this were the case, then the denominator would just be x squared plus 4. It wouldn't have to have a second degree power on it because these already have a common denominator, and there'd be no reason that it would have to step up to a degree 2. So one of these must be squared. Now, even though this becomes to the fourth power, it is still considered a repeated quadratic factor. And so in terms of what goes in the numerator for it, it doesn't have to be any more complicated than a linear function. If it's repeated quadratic, then a linear goes on top. If it's a quadratic factor, a linear goes on top. And if these are linear situations, then only a constant has to go on top. So the top here, since this is quadratic, it could be linear. And this, even though it's degree 4, it's really considered a repeated quadratic factor. And so you only need a cx plus d. We are going to do an example similar to this a little later on in this video. not these exact terms, but a different one. And last here is kind of, you would never have to do one as complicated as this, but I'm hoping it might help understand the difference between a repeated linear factor and a repeated quadratic factor. So try to think about what all the fractions could be that would have this as a common denominator. So if you had x to the third, you could have a fraction with an x on the bottom. You could have a fraction with an x squared on the bottom, and you could have a fraction with an x cubed on the bottom. All of those would have x cubed as the common denominator amongst them. And then with the x squared plus 4 cubed, you might have one with an x squared plus 4. You could have one with an x squared plus 4 squared, and you could have one with an x squared plus 4 cubed. Now, to decide what the numerator has to be, you have to be able to look at these and know whether they are quadratic factors, repeated quadratic factors, linear factors, or repeated linear factors. And this, I think, is probably the most confusing case, is that these are repeated linear factors. So the numerator for all three of these only has to be a constant. It's like having x plus 0 and x plus 0 squared and x plus 0 cubed. They're all repeated linear factors. Here, they're repeated quadratic factors, so this would need a linear something x plus something. Since I've already used a, b, and c, I'll have to use dx plus e, and fx plus g, and hx plus I. And that would be a ridiculous situation to solve out by hand, and nobody would ever make you do one that tricky. But that gives you kind of the structure of the type of problems here. And let's go ahead and try an example that has a repeated quadratic factor in it. Sorry, ran out of paper. So we are going to look at, let's just write down the algebra first. So let's do the decomposition for 8x cubed plus 13x over x squared plus 2 squared. So if I were going to decompose that, x squared plus 2 does not factor. Didn't really need those parentheses there. X squared plus 2 squared. And then in the numerator, since this is quadratic, I will need an ax plus b. And this is quadratic, so I will need a cx plus d. And then I'm going to multiply through by the common denominator here, x squared plus 2 squared, x squared plus 2 squared, x squared plus 2 squared. So these cancel entirely, so I get 8x cubed plus 13x, and one of these cancels, so I get ax plus b times x squared plus 2, and then both of these cancel, so I get just a cx plus d here. Now, the method we used in the previous example, where we could just substitute in a value and it helped find my missing letters of in the problem, that doesn't work so well here, because there's nothing I can substitute in for x to get this factor to be 0. So I'm going to use the method called equating coefficients that we did talk about during the school year, but we didn't ever really need it because we didn't have any ones that had these repeated quadratic factors in them. So I'm going to distribute this using binomial here. A times x squared will be ax cubed plus bx squared plus 2ax plus 2b plus cx plus d. All right, and then I'm going to do what's called equating coefficients, but I need to clean this up. And there's only one term that has an x cubed in it, and there's only one term that has an x squared in it. This is pretty friendly, but there's two terms with an x in it. So I'm going to factor the x out, and then there's two terms that make up the constant. So since this expression is true for every value of x, I can say that the a in front of the x cubed here, has to equal 8 because it's the only x cubed here. So a is equal to 8. There's a bx squared, but since there's no squared here, I know that the b is equal to 0. Then I also know that 2a plus c has to equal 13. And then I also know that 2b plus d has to equal 0 because there's no constant there. This is really 8x cubed plus 0x squareds plus 13x plus 0. And these coefficients have to equate to the coefficients over here. So I think I'll write that out a little more clearly. You could have thought of this as 8x cubed plus 0x squareds plus 13x plus 0. And then that would have equaled ax cubed plus bx squared plus 2a plus c times x plus 2b plus d. And then the 8 must equal a, the b must equal 0, the 13 equals 2a plus c, and the 2b plus d equals 0. And then that's enough to solve for these missing values here. We know that a is 8, and so this will be 2 times 8 plus c is equal to 13. So 16 plus c equals 13, or c equals -3. And 2b plus d equals 0, and b is 0. So 2 times 0 plus d is equal to 0. So 0 plus d equals 0, or d equals 0. Which means that my original 8x cubed plus 13x over x squared plus 2 squared is equal to a 8x, and b is 0, so this will be 8x over x squared plus 2. And here the c is -3, and the d is 0 over x squared plus 2 squared. Sorry, off the screen again, super annoying. All right, so then if this were a calculus problem, you would want to do the antiderivative of, if this had been then we could change it to that, and this should be easier to take the antiderivative of. And we do it on time. I guess we could take the time to do that and see how that goes. So if I were doing the antiderivative of this function, let's say x over x squared plus 2 dx plus negative 3 times the integral of x over x squared plus 2 squared dx. You should pause the video and just try this yourself, but here I could let u equal x squared plus 2, so du would equal 2x dx, and so 1/2 du is equal to x dx. Or another good trick that I don't think I ever showed you in class is, since this has an 8 on top, I could multiply both sides by 8 here and get 4 du is equal to 8x dx. And so then the integral here becomes 4 du over u. And then here, we probably shouldn't use the same variable that we did here in the same integral, but I'm just going to use u anyway. But you could say v or w over here. So if u equals x squared plus 2, then du equals 2x dx. So 1/2 du is equal to x dx. So this will become u to the negative 2, we've got a negative 3, a u to the negative 2, and the x dx becomes a 1/2 du. So I put a 2 on the outside there. All right, so then my antiderivative is the natural log of the absolute value of u, keep writing a plus, minus 3/2 u to the negative 1 times negative 1 plus c, and the u for this one is x squared plus 2. Since that is always positive, I don't need the absolute values, and this would be plus 3 over 2 times u plus c. And that is the final answer. All right, perhaps it would be good to look at one more example, but I'm not going to take the time to do that in a video for you. I did get these examples out of our textbook, Larson Calculus, 8th edition, and the third example, if I were going to do one, would be example 3 on page 556. And it looks like, if you wanted to try it on your own, it is x squared minus x and x squared plus 4 and 2x cubed minus 4x minus 8. Wouldn't necessarily do all the calculus for it, but you could consider doing the partial fraction decomposition for it and at least trying to get the setup of what it would be. You would definitely want to factor this, x squared minus x. Even though it looks quadratic here, you could factor that into 2 linear factors rather than a quadratic factor. One thing to note, if you don't recognize something as like a repeated linear factor, say this question just had the x and the x squared, and you put, say, a bx plus c on the top, you would still get to the right answer. It's just the algebraic work to do the partial fraction decomposition will be harder than necessary. So if you accidentally don't recognize the benefit of a repeated linear factor, you won't necessarily get it wrong, you'll just do more work. So you'll appreciate being able to recognize repeated linear factors. All right, thanks for watching.